Hi, my name is John Krochmally, and I've created these video modules for people needing to understand and apply their skills knowledge to install, service, and maintain technology controlled by automation systems, and particularly the Programmable Logic Controller. Programmable Logic Controllers, or PLCs, are frequently found in many applications involving automation and instrumentation. In this presentation, we will cover the typical power wiring associated with a common programmable logic controller. We will also explore various troubleshooting techniques necessary to determine and correct problems related to the powering up of the PLC assembly. There will be 4 learning outcomes to this presentation. Number 1, identify PLC power terminals. Number 2, provide power wiring to the PLCs. Number 3, measure power supplied to PLCs. And number 4, troubleshoot common PLC power problems. Programmable logic controllers, or PLCs, come in a vast array of sizes. The Allen-Bradley Compact Logics, Micrologics, Control Logics, SLC500, and the Omron Mini PLCs are usually rack-mounted and come in various combinations consisting of input and output modules. PLC power supplies take a supplied voltage, usually 120 volts AC, convert this voltage down to DC voltage that the PLC assembly will use, and then distribute this DC reduced voltage to other PLC assembly areas. Notice that the Compact Logics, Control Logics, and SLC500 PLCs have separate and distinct power supplies, central processing units, or CPUs, input and output modules. Highlighted here are the locations of the PLC power supply for the Allen-Bradley Compact Logic, Control Logic, and the SLC500 PLC assemblies. Other programmable logic controllers could be considered brick PLCs in that the power supply, central processing unit, inputs, and outputs are all in one module. We can see that the Omron Mini PLC and the Allen-Bradley Micrologics PLC represents one item, and their terminals are associated with power inputs, outputs, field devices, and others specific to the intended use of the PLC. In this graphic, we see the Omron DC12-24 volt Mini PLC on the left, and the Allen-Bradley Micrologics located on the right. These photos offer a closer look of a typical brick PLC. These types of PLCs will have a source of power, maybe 120 volts AC, or could be 24 volt DC or 12 volt DC, connected to them. This sourced power voltage is then converted into the PLC's operational power with an internally housed circuit power supply that provides operational power to the system. Power provided to a typical PLC assembly usually comes from 3 or more providers. At the bottom, we see L1 is supplying 120 volts AC to the PLC power supply. L2 is supplying 120 volts AC to the PLC input module located at the left of the graphic. And L3, to the right of the graphic, is supplying 120 volts AC to the PLC output module. In this presentation, we will be referring to this print showing the layout of a typical PLC with its power supply, central processing unit, input and output units. Referencing this drawing, notice at the bottom of the print, power L1 is brought to the PLC power supply. The N for neutral and G for ground are also shown. These represent the intended 120 volt AC of supplied power to the PLC assembly only. Typical electronic circuits operate on voltage pressures of direct current and may be less than 24 volts DC. The initial power making up these lower voltages usually come from a utility-supplied 120 volts AC. The duty of any power supply is to convert an electrical power AC to an electrical power DC. In this graphic, we see that the power supply accepts 120 volts AC from a power source. This PLC assembly power supply transforms the 120 volts of power into 20 volts DC. This reduced power is then supplied to the PLC assembly electronics, which in turn supplies the reduced power to the processor input and output modules. Notice the presence of a green power LED lamp on the power supply module. This LED illuminates in the presence of electrical power. This LED and others located on the PLC assembly are considered diagnostic LEDs and can be used in PLC maintenance, troubleshooting, and servicing. Researching the PLC manufacturer's assembly documentation will provide further information regarding the LED's purpose, how the LED lamps signal unit malfunction, and how to use these in the troubleshooting process. In the Omron Zen Brick PLC, we connect 120 volts AC to the associated power supply terminals, shown as L1 and N. With this 120 volt supplied AC voltage, the powered conductor, usually black in color, is wired to L1 terminal. The grounding conductor, usually white in color, is wired to the N or neutral terminal. Many PLCs will be manufactured to accept more than one voltage source. In this graphic, the PLC could also be wired to a 240 volt AC power source. In this application, a neutral is not needed. The power coming in from L1 and L2 sources are connected as shown. Referencing the Allen Bradley Micrologics PLC, we see similar power wiring arrangements. The powered, usually black conductor is wired to L1. The grounding, usually white conductor, is wired to the L2 and neutral terminal. A grounded terminal, identified with its symbol, or as G for ground, is available for electrical safety purposes. If 240 volts AC is the source voltage, then the L2/N terminal receives the L2 conductor power. Referencing the Allen Bradley SLC500, the power supply is provided to its own module, usually located in the array extreme left side. Power, neutral, and grounding terminals are identified and are located towards the bottom of the terminal block. Notice the wiring instructions located on the power supply module's door and the associated wiring patterns. The bottom terminal is for the ground conductor, usually having a green-colored insulation. Above this is the intended location for either the neutral for 120 volt applications or for the L2 voltage for 240 volt applications. Third from the bottom shows the location of the intended 120 volt AC for the L1 voltage conductor. Similar to the SLC500, the Allen Bradley Compact Logic PLCs have their power supply in its own module. Note the wiring instructions located on its access door. This graphic shows a PLC needing 24 volts DC power provided to it. This arrangement requires the use of a field-installed 120 volt AC to 24 volt DC power supply to provide the power to this PLC. In this application, the solar power supply 120 volt AC to 24 volt DC converts its supplied 120 volt AC power to 24 volt DC power and then supply this power to the Micrologic's Programmable Logic Controller. Notice the wiring patterns to achieve the necessary power to the PLC. 120 volt power is supplied to the solar unit at the bottom. The 24-volt DC power is taken off the top of the solar unit and provided to the PLC. Troubleshooting the PLC supplied power involves the use of a voltage-configured multimeter. If the proper power is applied to the Micrologix PLC on terminals L1 and neutral, the measured voltage should read 120 volts AC. Referencing the Omron Zen PLC, the voltage-configured multimeter should read 120 volts AC if supply voltage is applied. For the Allen Bradley Compact Logix, the assembly's power supply has its own module. Opening its access door reveals the location of the power supply wiring. A voltage-configured multimeter will measure 120 volts AC if power is being applied to this unit. Many PLC rack-mounted assemblies have separate processors, input modules, and output modules, and will have their own power supply with an over-amperage protection fuse. Checking the fuse for integrity involves placing a resistance-configured multimeter across the fuse. A good fuse should measure 0 ohms of resistance. An open fuse should measure OL, or open line, and therefore needing replacement. It is important to understand that if a fuse is open, there exists in the circuit a higher than normal amperage situation that must be identified and corrected.